Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel for all things math and science, or at least what I want to talk about. And what we're going to be talking about today is chemistry, the concept called stoichiometry. So I have made some notes that we're going to go through on my smartboard, okay? So the question is, how much? How much does a reaction make? A chemical equation is a recipe. And how do you get that recipe to actually making stuff? Well, it's this weird word. Now, I say it stoichiometry. One of the other teachers here really emphasizes the oi. He says stoichiometry, which is probably more correct, but either way, you can call it what you want. And it is how you use the balanced chemical equation, the coefficients, that tell you the number of moles, and that's what we did last time, was balancing chemical equations. It'll tell you the number of moles, and it's what they tell you, and they really tell you how much to go get. In my lab here, what I do is I use a balanced chemical equation. I use the periodic table to translate the balanced chemical equation to grams, and I go weigh out how many I need. And here's an example. This is the chemical reaction for making banana flavoring. So we did that in chemistry in the class I teach yesterday. And so we drew a banana on here because that helps you remember. There's the banana, okay? So step one, I'm going to go through the steps first, and then we'll apply it to problems. Step one is write a balanced chemical equation. So here's my equation. We'll check and see if they're the equation for banana flavoring. Then you write what you know and don't know underneath the chemicals. Then you use conversion factors to make sure your units are consistent. Now, I reviewed with people how to convert a day into seconds. You write what you know first. You write the units of what you know in the denominator, and then the units that you want to change it to in the numerator. But because I don't know how many seconds are in a day, I had to go through hours and minutes and then seconds. Anything in the numerator, if you have the same words in numerator and denominator, you can mark them out. If the numbers you don't mark out. Any number on top you multiply, see my dot for multiply. Any number on bottom you divide. Okay, next step is usually what you do in these problems is you look up on the periodic table the molar masses. That's the decimal number. So go find that decimal number, round it off, and add them up. And write it underneath what you know and don't know. You don't have to do them for all the rest, just for what you know and don't know. And I call the molar mass the M&M. And in my class, we colored them. In fact, I should do that now. Draw, let's make it a nice color. Let's see if it's going to, yes, oh, look at that. I'm turning my M&M red. All right, just have to have fun. All right, so now we'll stop that. We'll undraw, undraw, undraw. I don't know if I can undraw or not. Anyway, then what you do is you look at the balanced chemical equation and you write a mole ratio, okay? And then you draw a U, a big U. I say it looks like a smiley face, so it's all happy. And then you set up your conversion factors, and I like you to set it up like train tracks. So I drew some, oops, let's see if I can get it to, I think I'm gonna have to run over here real quick because I've played with it with the drawing thing. Sorry about that. I will be right back, and I'll show you our first example problem. Okay, hopefully you can hear me say that. Okay, so you draw your train tracks, and I like this better than parentheses, and then you do the math. Okay, so here's our example. You have 45 kilograms. Remember I said you need your units consistent and you need them in grams. So we can use King Henry's Daughter bakes delicious chocolate muffins, and we're moving from kilo to the basic unit of gram, and it's 1, 2, 3 frog hops. It's the frog the princess kissed. You can watch Princess and the Frog if you need to update that. And so you move your decimal place 3 places, 1, 2, 3, and it makes up 45,000 grams. Isoamyl alcohol and enough acetic acid to react with it. How much banana flavoring can you make? So the first thing is what we know. We know 45,000 grams isoamyl alcohol, that one. We have to look and see what it is. And what we don't know is how much banana flavoring, C7H14O2, we can make. So that's what we know and what we don't know. Then we look up the molar mass. So on the periodic table, I'll look up and I see that carbon is 12. I multiply it times 5. Hydrogen is 1. 1 times 12 is 12. So I do whatever carbon is plus 12 more. And then oxygen is 16. I add them all up and I get 88 grams per mole. You don't do anything with the coefficient. There could be a 2 there, a 5, it doesn't matter. You don't do anything with it when you figure out molar mass. We also get the molar mass of this, the C7H12O2, and write it there on our M&M line. And then we might write the mole ratio. From the balanced chemical equation, it's 1 to 1. Now we set up our problem. We start with what we know. That's what I always tell the kids. What do you know? Okay, and that's 45,000 grams with the units. Grams of isoamyl alcohol. The unit that is here goes down here. So this is grams isoamyl alcohol. And the number that goes with grams, you follow this U around from what you know to what you don't know. And the next number here is 88. So it's 88 grams of isoamyl alcohol. What goes in the numerator is this mole. This is a ratio, grams on the bottom, moles on top, and the number that goes with that mole is an understood 1. So this is 1 mole of isoamyl alcohol. Then comes your mole ratio. This 1 is moles of isoamyl alcohol. It goes on the denominator. You always do denominator first. So it's grams of isoamyl alcohol, grams of isoamyl alcohol. Moles of isoamyl alcohol, moles of isoamyl alcohol. What goes in the numerator is this 1, and it's moles of banana flavoring. I put mole BF, banana flavoring. What goes in the denominator here is moles of banana flavoring. It has to be the same thing that's in the numerator here. And it's that mole right there is where it's coming from. Then what goes in the numerator is 130 grams from right here. Grams of isoamyl alcohol mark out, moles of isoamyl alcohol mark out, moles of banana flavoring mark out, and I'm left with what I was supposed to have, grams of banana flavoring. Any number on top you multiply, any number on bottom you divide. This is how I do my calculator. I do 45,000. You don't have to do the ones. Anything multiplied or divided by 1 is itself. 45,000, and then I'd say times 130, enter. Then I'd say divided by 88, enter. And if there's any other numbers that aren't 1, I'd say divided by that, enter. And that's how I would get it. And that's what it is in grams. If we wanted it in kilograms, we would do that. Let's see if I can. If I can take off draw. Let's see if I go home. Sorry, I'm going to have to roll it up over here. I had to play with it and get that pink lighting and messed it up. So let me fix it now. Whoop, here comes our next one. Okay, so here's another problem. This one we're going to make oil of wintergreen, and we did that in lab yesterday too. So we're going to take methyl salicylate, is known as oil of wintergreen. It's made between a reaction between methanol, which is that, and salicylic acid, which is that, and that's the methanol and that's water. So we're told that we want to produce 325 grams of methanol, and we want to know how many grams of salicylic acid are needed. So we write a question mark under the salicylic acid. We write what we know underneath the wintergreen. We look up the molar mass for both of them and add it up. We write the mole ratio, and once again, it's 1 to 1. We draw a U. Start by putting a dot by what you know, and draw an arrow around to what you don't know. And that lets you know what you write next on your train track. So we start with what we know, 325 grams of wintergreen. We put the molar mass, grams of wintergreen, 152 on the bottom, mole from right here on top, mole of wintergreen. The moles of wintergreen down here, it's that one right there, because it's what comes next on your arrow. Moles of salicylic acid, I just put A for acid, comes from that one right here on top. Moles of acid is that mole right there. And then grams of acid go right here. Any number on top, you multiply. Any number on bottom, you divide. And try it on your calculator. Pause the video, try it, and see if you can get 295 grams of salicylic acid. Okay, let's do the next one. Y'all are doing great. Hanging in there, especially with me having messed up the little thing where I have to roll it up. All right, let's do our third problem. Our third problem says, how many moles of water, so I'm going to put question mark mole underneath water, are produced by 14,000 moles of hydrazine rocket fuel? Ooh, that sounds interesting. And first I asked how many moles and then grams. So I did the problem twice. The first time was when it was question mark moles in blue. And first I had to balance the equation. Because it's just moles, we don't need the molar mass. We only need the molar mass when it asks for grams or has grams. So I tell the kids, imagine yourself a delicious graham cracker. Imagine you put peanut butter on it, and then imagine you put a handful of M&Ms on it. So grams go with M&Ms. Grams go with molar mass. Now imagine eating it. Now I don't like plain M&Ms, but peanut are pretty good. Peanut butter are okay. I ate too many one time and got sick of them, but I really like the new brownie ones. And I'm not even sponsored by them. Okay. So now we can do our problem. We start with what we know, 14,000 moles of hydrazine. We go around our U, and next comes 2. So 2 moles of hydrazine go in the denominator first. What goes in the numerator are 4 moles of water. Water looks like unimpressed Mickey Mouse. And now the moles of hydrazine mark out. We multiply what's on top, divide by what's on bottom, and we get 28,000 moles of water. Okay? Now we're going to do it again, but this time for grams. So if we have grams, we need our graham cracker molar mass with M&Ms on it. So the molar mass of water is 18. 16 plus 1 plus 1 is 18. 18 grams per mole. So this time we go around again, starting with what we know, 14,000 moles of hydrazine. Moles of hydrazine go on the bottom, it's that 2. Moles of water go on top, it's the 4. Then as we come on around, moles of water from right there go on bottom. Grams of water from right there go on top. So multiply everything on top, divide by what's on bottom, and I got 504,000 grams of water. All right, let's do the next one. Next problem. I know this just is great TV, isn't it, with me, the star of the show, walking off. Okay, here's our next one. Find the mass of sugar required to produce 3 liters of carbon dioxide gas. Now, if you don't have grams, you don't do molar mass. So here we have liters. We're still going to start with balancing our equation. Balance, check. Then we're going to write what we know, 3 liters, and what we don't know, how many grams. We have grams here. Grams means M&Ms. So we need to look up the molar mass, and the molar mass of sugar is 180 grams per mole. But here we don't have grams, we have liters. So we have to go back to the unit where we learned about moles, and we learned that a mole of any gas is 22.4 liters. 22.4 liters per mole is what goes on the M&M line if it's not grams, and it is asking for liters. There's something else if it's molecules, particles, that we'll do in our next problem. Okay? So, and then our balanced chemical equation ratio is 1 to 2. Understood? 1 to 2. That's where the coefficients come in. So if I'm doing the molar mass of this, it's just the molar mass of carbon plus 2 oxygens. You do not use that 2 right there. Hold on. Talking too much today. Need some water. Oh, and I think I'm out here. Okay, so now we've got our thing. We make our U from what we know to what we don't know. We start with what we know, 3 liters. We put in the denominator liters of carbon dioxide, and the number that goes with it is 22.4. What goes in the numerator is 1 mole. 1 is understood. We have to be cool like math. They have understood 1, so we want them too. And then we keep moving around. Moles of CO2, that 2 goes on the bottom. Moles of sugar go on top, 1. Then moles of sugar from right there goes there with the understood 1. And then 180 grams goes right here. Any number on top you multiply, any number on bottom you divide, and you should get 12 grams. So that's what you do if there is a gas. You use that 22.4 liters. Now, this time, it's atoms, molecules, or particles. If you have atoms, molecules, or particles, then you use, he's Italian, he's a physicist and a chemist, and he's your favorite, Amadeo Avogadro. Avogadro's number, otherwise known as 6.02 times 10 to the 23rd. I used to teach out of a book that did 6.022 times 10 to the 23rd. I carried it out another decimal. All right, so we're going to write what we know. We balance our equation, check. Then we write what we know, 6 grams of water. Underneath water, we write 6. Underneath what we don't know, molecules of hydrogen, question mark molecules. This is grams, so we do molar mass for water is 18. But this is not grams, it's molecules. Atoms, particles, or molecules, you do Avogadro's number, 6.02 times 10 to the 23rd, molecules per mole. We write our mole ratio from the balanced chemical equation, 2 and 2, and now we start with what we know and go around to what we don't. 6 grams divided by 18 grams times 1 mole, then that 2 goes right here, this 2 goes in the numerator, you keep going around, that mole goes down here, Avogadro's number goes on top. Grams cancel out, moles cancel out, moles cancel out, you're left with the molecules. The answer is 2 times 10 to the 23rd molecules of hydrogen. All right, let's do our next one. We're doing good. Sorry about having to run off and move the problem up. Okay, here's our next one. And this is, sometimes you have something called a limiting reactant. I always say it's like brownies. Imagine that I've been told that I need to take brownies to a party, and I go buy 4 boxes. But when I get home, I only have enough eggs to make 2 boxes. So eggs were my limiting reactant. I can really only make 2 boxes. With limiting reactant problems, you will be given 2 knowns. This time I'm given carbon dioxide and hydrogen. And 1 unknown. What you do is you do the problem twice. I did it once for carbon dioxide and I did it once for hydrogen. You look at the answers and whichever one is less is what really happens. 174 grams is less, so that's what really happens, and carbon monoxide is what limits it. So that's the limiting reactant one. Okay, so you can look through that. Take a screenshot, make sure you understand how I did it. Now, sometimes you don't get as much as you want. Say you're making brownies and you spill some mix on the floor. What do? You don't get as much as you were supposed to. Well, that happens in lab too. Sometimes you spill some chemical on the floor. Sometimes you don't dry it out enough. Sometimes you dry it out too much. So you have to do a calculation called percent yield. And it's what you actually got divided by what you were supposed to get times 100. So if we really only got 150 and we were supposed to get 174, you do 150 divided by 174 times 100, 86%. We did all right. And then sometimes in lab, in college, they'll make you redo it if you don't get a good enough, percent. Okay, now what factors affect a chemical reaction? Things like temperature, concentration, and pressure do. If you heat it up, sometimes it goes faster. Put more in, goes faster. Pressure, that's everybody buys the Instant Pot now. Why? Make it go faster, right? All of them, why does all those things help? It's because of collision theory. If you increase the temperature, the particles move faster. If you increase the concentration, there's more of them there. And if you increase the pressure, they're all of these things are making them more likely to collide, which makes them react better. There's a guy named, I call him Le Chatelier. Now, my son said I'm pronouncing it wrong. I'm sure that's perfect French, right? But anyway, he came up with the idea of how these affect, and also with reactions. I'm going to have to go to class now. With reactions, sometimes they need a little help, like striking a match. And that is called the activation energy. Sometimes you need a little more energy to make them go, and sometimes you need a catalyst to make them go. Add another chemical. We saw it in lab when we added manganese dioxide to hydrogen peroxide, and it helped with the decomposition reaction. Le Chatelier also is if it's equilibrium, you can push things more toward reactants or products. Depending, if you can add more concentration to one side, it'll push it to the other. Also, temperature and pressure can push reactions back and forth. All right, you can look up some more videos about that if you want to know more. Math is great, science is great. Come back and watch some more. Like, share, subscribe.